Let's use this video to delve a little deeper into the capabilities of the 9404 Sampler Extended Real-Time Oscilloscope. Let me show you three things that you can do with this valuable and versatile little instrument. So I thought we'd take a look at a fast impulse measurement. Routed through to channel 1, I have a narrow and rather small amplitude pulse. It's around about 90 millivolts peak to peak. If we look at the top of our screen, our trigger rate is about 200 kilohertz at the moment. So this is a fairly slow repetition rate pulse that we're looking at. And at this particular time-based setting, as we can see at the top of the screen, I'm running at 1 terasample per second. That's 1 picosecond sample interval, and I've got 250k samples writing to the screen at the moment. So heavily oversampled noise at the top of the screen on this relatively small signal. Okay, so let's take a look a bit closer with the zoom facility. We'll enable zoom 1, and if we pull the box across here, so I'm setting a horizontal factor of, let's go a bit further, 50. Let's pull that back a bit to 100, 200. A zoom factor of times 200 at the 50% trigger position. Let's get some measures on. Measure, statistics, channel 1. Let's have fall time, rise time, amplitude, negative jitter, peak to peak, and RMS. And let's also have negative width. There we go. And as we have added the measurements, the thresholds that are being used in the measurement are being displayed on the screen here. And also the last measurement, the width, we can see where the width is, the pulse width is being measured. Now, in most of my experience, when I've come across impulse measurements, the scientists that tend to make impulse measurements generally use the 30% mesial to define pulse width. So in this case, this would be, in this inverted case, the 70% mesial. So let's move that up to roughly 70%. And then within the measurements menu, the user definitions, I can set the threshold exactly to 70%. So now my pulse width, negative width, it's currently measuring 197 picoseconds. Let's move this to a slightly faster time base. Now we're getting a negative jitter peak to peak measurement and an RMS measurement there. Let's sort out our zoom box. We don't need quite so much magnification on that now. And there we are, approaching 3 picoseconds RMS jitter. Of course, one of the many things you might want to do with your 9404 is to look at data eyes. So what I've done here is I've connected the 9404 up to a pattern generator, and I'm using our Agile synthesizer, the AS108, to clock the pattern generator. So let's see what autoscale makes of that batch of signals. And there we have them. Okay, so I've got clock at the top, The clock is set at 1.25 gigahertz at the moment on the AS108. Let's slow that time base down a little bit, and we can see now on channel 1, if I trigger on channel 1, I've got my clock, sinusoidal. On channel 2, I've got my data stream. On channel 3, I've got my pattern trigger, and if I slow the time base down a little bit further, there we go, we can see the repeating pattern. It's a 2 to the 7 pseudo-random bit sequence, and on channel 4 I've got clock divided by 16. And we will speed this time base up, and we can see that our data eye is forming on channel 2, and really at this point we can lose interest in all of the other waveforms. So let's turn off channel 1, let's turn off channel 3, channel 4, and let's put our display into single YT mode. Okay, we are now ready to add our an eye mask to this. So as I say, we're running at 1.25 gigabits per second. I'm going to add an eye mask. We can see here we've got a number of masks available to us. I'm going to use an Ethernet mask, and I'm going to select from the list 1.25 gig mask, and let's build it. And then let's align to it. There we go. Now we can begin testing this waveform against the mask straight away. If I just select its channel 2, and we test channel 2 against the mask, and I don't know whether you can see this, but there is a little tiny grazing of the mask there, and you can just see 1 or 2 red points appearing on polygon 1. And down here we have begun counting statistics here, so we can see the total number of waveforms that have passed through here, and the failed sample count on the total failed sample count, and those failed samples on polygon 1. In fact, I can just see there are a couple emerging here in this corner as well. Okay, so let's change the frequency to 2.5 gigahertz, 2.5 gigabits per second now, and well, that's certainly caused quite a few failures against the mask. Let's change the mask to 2 times gigabit Ethernet, and realign. There we go. And we can run channel 2 against this mask, and you can see here we're beginning to get hits on number 3, polygon 3, and again my count is rising here. I can add a user margin to this mask, so we can add a margin to stress test any given mask. Here we go, and of course if I re-establish the test, we are now heavily failing against polygon 3, and we can see what margin we've got against the other masks, and you can see I'm just beginning at 60% margin. I'm just beginning to hit the let's go down a bit, just beginning to hit the other polygons there. So I've got an infringement on 2 and an infringement on 1 here, with a 55% margin added. Now what else can we do? We can add a set of measures to this. So to select none return to 0 on channel 2, you can see I've picked up a large number of standard measures that I can apply to this eye. I'm going to apply bitrate, jitter RMS, and you can see as I add the measurements on the display we're getting an indication of where jitter RMS is being measured. let's add signal to noise ratio, and again the indication as to where it's being measured. Let's add 1 level and 0 level, and there we go. So here we have a 2.506 gigabit per second data rate. We're looking at jitter RMS as being about 3.3 picoseconds, 3.2 picoseconds, signal to noise ratio 25.46 dB, and the 1 level and the 0 level are, well, slightly lower on the 0 level at -137, and on the upper level 1 we're on 133 millivolts, so not quite symmetric there. I can, by using the AS108, I can just put a little bit of a frequency hop on here. I'll just do that to force some jitter into the picture here, and you can see, can't you, how the variable persistence display is beginning to show us some systematic jitter on this eye. So we can bring a little more clarity to the picture here if we choose to add a histogram to channel 2 horizontal, and here we can see that's just beginning to build there, and what we're going to see build is a bimodal histogram at the 2 locations. And you notice down here in the readouts box we've got a whole collection here of statistics around that histogram. Peak to peak readings, medians, means, maxes, mean plus or minus a number of standard deviations there. So comprehensive information around our histograms. We can also improve our display to a degree. We can use infinite color grading, and now we will have color contouring to the number of hits there in each position of the eye. So comprehensive analysis there for your data eyes. So here I've switched to a signal from our new AS108 Agile synthesizer. I've got the RF output connected to channel 1. I've got a sweep trigger output connected to channel 2 of the 9404. The AS108 is generating a sequence of 16 QAM levels at 900 megahertz carrier. It's just a repeating pattern of the levels associated with QAM. And then on the screen here I'm now displaying on channel 1 the envelope of the carrier pattern, and on channel 2, there you go, you can see the trigger pulses at the beginning of each pattern cycle. Now this is a real-time envelope of the pattern that I'm displaying here. The carrier highly aliased, of course. If we histogram this envelope and draw the histogram box out here to cover the entire pattern of levels, we can now turn on our markers, Y markers, and if we align those with the histogram peaks, we could in turn measure each of the carrier levels associated with the pattern here. If we now begin to speed up our time base, we've now moved into ETS acquisition from our previous real-time acquisition, so we're now using equivalent time sampling, and I'm going to take this all the way up to 200 picoseconds per division, 1 tera sample per second now. At this point we need to move over to trigger on the carrier, and there we are. We've moved from focus on the pattern to focus on the carrier. So now we're seeing our modulated carrier, and our histogram is re-established exactly as it was for the pattern. Let's bring on the controls for the generator here and change the frequency to 2.4 gigahertz, and then clear the histogram. So I've changed the carrier to another one that would be very familiar to us all, I'm sure. As you can see, our histogram levels have changed very slightly. Let's line those markers up again, and then we can go all the way back down the time bases. Go back to 200 microseconds per division, change our trigger channel, and our pattern will re-emerge. So now there is our envelope at 2.4 gigahertz. Now this is the sort of capability that we might use when testing envelope track power amplifiers, for instance, perhaps displaying a modulation envelope on channel 2, the envelope track on channel 3, and maybe supply current on the 4th channel.